Hello, everyone. Welcome to the seminar for today. So it's my pleasure to introduce Volodymyr Takhistov from the Kavli IPMU in Tokyo. So Volodymyr originally did his PhD at UC Irvine before moving to do a postdoc at UCLA, where he was for several years. And he's now the Kavli Fellow at the Kavli IPMU in Tokyo. So Volodymyr has worked on a very, very wide range of topics, from dark matter, neutrino physics, all sorts. So he's an expert on many of these fascinating ideas, which you can see encapsulated in his wonderful title for the talk. So thank you very much for being with us, and why don't you go ahead?
Thank you very much, Aaron, for the kind introduction. Thank you very much for the opportunity to speak, although virtually. So I will discuss today a variety of topics, as Sharon already kindly mentioned. So let me start with just outlining some general things. And of course, we're all interested in thinking about big questions. And one of them is, of course, what is the universe made of? And as we all know, that the predominant constituent of matter is in this mysterious substance, so-called dark matter. And we're all very interested in finding out what it is. Well, what do we know? We know where is it, how much of it, and what is it doing and not doing partially, although all evidence is astronomical. Well, what do we want to know? Well, we want to find out what is the origin of this mysterious substance, and if its constituents are particles, what are the types and masses of these particles, and are there interactions beyond gravity? Of course, as we all now know, there's actually a vast ocean of possibilities that can answer these questions. Now, the traditional searches can be roughly broken down colloquially into make, shake, and break, where the make would correspond to production of dark matter, in particular when the two standard model particles interact, and you somehow create dark matter through this interaction. This is particular, of course, pronounced in colliders, for example, the LHC, and then you try to search for various signatures this way. The shake is roughly associated with direct detection, where here the idea is that you have some laboratory experiment, and dark matter comes in and somehow interacts within your detector, deposits some energy in some way, and you try to look for signatures in this way. And finally, the break is associated with so-called indirect detection. And here, the idea is that dark matter particles somehow interact and produce resulting standard model particles, which then you can, in principle, observe. And so you can take your nice instruments, such as the Fermi Space Telescope, and look for places of abundant, of where the dark matter is expected to be abundant, such as the galactic center, and try to look for signatures from such kind of processes. Of course, there's very many different ideas that have been proposed for the various detections. Let me just outline one particular example associated with super Kamiokande and by extension Hyper Kamiokande. Now, as we know, Super K is a leading large underground neutrino experiment located in Japan, in the Kamioka mine. It is, of course, a place of great neutrino science, and here the neutrino oscillations were discovered in 1998. It is also a place of doing exciting astroparticle physics, as well as looking for tests of unification theories through very number violating processes. to which I have also directly contributed to these searches. And the bounds from Super K, of course, the best in the world for these kinds of things. There is also a place to do very good indirect dark matter detection studies, as highlighted by this recent study from Bell, Dolan, and Robles for the case of Hyper Suprime-Cam. Now, aside doing the more conventional direct dark matter detection searches, which can be associated with the dark matter somehow interacting and producing some neutrino fluxes, so that you can try to detect them. You can also try to utilize such big, powerful general experiments to do other kind of searches as well associated with dark matter. For example, let us consider that there is dark matter component X that has a small electric charge, so-called millicharge, and for the review on with some interesting things about quantization, please see the work by Robert Food, Raymond Wolkes, and Lou. And one interesting way one can study these things in Super-Cam is if you consider so-called atmospheric collider. And here the idea is that the cosmic rays will bombard the atmosphere. And of course, this is how you produce atmospheric neutrinos through meson decays, which then you can study. But if you also have these small charged dark matter particles in your model, you can also produce them in a very similar way. And then again, you can use your nice big experiments such as Super K to detect them. Another related idea is to use cosmic accelerator. And here the idea is that to accelerate within the vicinity of the supernova remnant, accelerate these small, these dark matter particles with small electric charge, and again, use your big experiments such as Super K to detect them. Now, of course, while there have been a lot of prospects and proposals and searches, there is no convincing science for dark matter thus far. And obviously, we hear from time to time about exciting accesses such as ZN1000 and so on, but there is no convincing science thus far. And we want to go beyond what has been done so far and probe dark matter deeper. So let me briefly discuss large direct dark matter detection experiments. And here the idea is that you look for particle dark matter interactions in the detector, and then you look for nuclear or electron recoils. And the typical setup can involve a heavy target material with a sizable atomic number. These are very low threshold experiments. Very low here means of order keV. And these are potentially scalable, especially if we're talking about experiments based on argon or xenon, which means that dark matter experiments that have very low threshold can in principle have significant fiducial volume. Now, the generation 2 experiments are ton scale, but generation 3 experiments are expected to be multi-ton scale. So this is already quite significant fiducial volume for such experiments. And let me just mention for reference that proposals such as those, such as Argo or Darwin, are already above the 50-ton mass scale ranges. Of course, if you do see a signal at some point that is convincing within some particular experiment, you can do all kinds of interesting analyses. So the standard analysis is so-called halo-dependent analysis, where you assume the local dark matter halo properties, and then you can make a nice plot in terms of the dark matter particle parameter space in terms of cross-section mass. Conversely, you can do a halo-independent analysis and try to infer the properties of the local dark matter halo. And I would like to point out that actually in this recent work with Graciela Gelmini and Moping Chen, we presented the first way how such analysis can be applied to electron scattering. So let me now discuss the connection between neutrinos and dark matter in the context of such large experiments. Now, as you will probe deeper, and this is of course what we want to do, given that we have no convincing signals thus far, big dark matter experiments will start to eventually encounter contamination from neutrinos. And actually, this constitutes an irreducible background. So this is associated with neutrinos coming from the sun, from the supernovae, from Earth. These are the geoneutrinos from cosmic rays. And collectively, all these represent irreducible neutrino background, colloquially called so-called neutrino floor. And I would like to point out that some of the local experts have contributed important work to the studies of this. Now, let me now illustrate what is the effect of this on the dark matter searches. So here is a combined neutrino sources flux plot from one of my studies with Graciela Gelmini and Sam Witte. In the case of a snow lab location, but this can be trivial extended to other laboratory locations. And here on the x-axis, you see neutrino energy. On the y-axis, the neutrino flux. And you can see that there's very many different contributions of the different sources that can serve as background. Primarily, these are contributions associated with solar neutrinos. Now, what is the effect of this on dark matter searches? Well, one representative case can be shown here on the right for the effect on the dark matter discovery reach. And this is in the context of large xenon type direct detection experiment, where the interaction is spin independent. And on the x-axis is the mass of the dark matter particle. On the y-axis is the reference cross-section that you're trying to probe. The different lines right here correspond to different exposure, or equivalently more data and larger experiment with larger running time. And what you can see right here is that with neutrinos, as you try to probe deeper with bigger experiment or more data into your dark matter parameter space, you sort of get stuck into this point right here. Even though you have collected more data or considered higher exposure, and this is just the fact that you got hit by a solar neutrino background, which mimics dark matter and is difficult to overcome, so you are not very sensitive. And this illustrates the fact that bigger experiment does not necessarily imply better sensitivity. Now, as we see that neutrino sources can be a problem for dark matter searches in the conventional sense. However, we can think of this problem in a different way, namely to think of using these big dark matter experiments as effective complementary neutrino telescopes. And so this is actually an opportunity to do interesting neutrino physics. So let me mention one interesting possibility how to do neutrino astronomy with such dark matter laboratories. And this can be illustrated for the problem of trying to unravel the origin of supermassive black holes. However, this can also be applied to a lot of other very interesting problems. For example, trying to do supernova forecast with pre-supernova neutrinos. The idea here is try to detect neutrinos that come out before the main core collapse event and try to forecast the main event this way. Or one can also do such things as trying to explore the Earth's formation and composition using geoneutrinos. So let me mention some things about supermassive black holes. Of course, we now know definitively that they exist. In particular, supermassive black holes are massive engines that power quasars, especially the high redshift quasars. And here you can have black holes of order 10 to the 9 solar masses, so really humongous. We also know the supermassive black holes exist within galactic centers, and this has been commemorated by the 2020 Nobel Prize. And let me now just show you a movie from the UCLA Galactic Center group illustrating motion of objects around the galactic center. And as you can see from the various orbits and wiggles, there is a massive object right here, and this is the supermassive black hole in the center of the Milky Way. Now, this is, of course, all great, but then the obvious question is, well, where do such huge black holes come from? And this is turns out to be quite a major problem in astronomy. So one natural consideration is perhaps you can start with a small baby black hole, for example, let's say a solar mass black hole, and just vigorously throw stuff in it and feed it and try to grow it to a humongous black hole. Well, it turns out that even if you feed it very vigorously, it is very difficult to achieve humongous black holes on reasonable galactic timescales. Well, an alternative is to start with a sizable seed and then grow that seed instead. Well, if you look at the various standard pathways considered in astrophysics for formation of massive black holes, and this is from a well-known review of Begelman and Martin Rees, you can see that a variety of the pathways, such as some gas cloud collapse, some dense star cluster collapse, and so on, they lead through an intermediate supermassive star phase. And so it seems that a variety of pathways predict that there are these massive, and here massive means bigger than 10 to the 4 solar masses, stars. Okay, well, how can you test such a possibility? And here is where we can again try to exploit neutrinos, as has been shown in this study of mine with Victor Munoz and Vite and George Fuller. Now, the supermassive star collapse releases enormous total energy neutrinos. In fact, it is several orders bigger compared to the conventional supernova. However, even though you release prodigious amount of neutrino flux, the individual neutrinos are low energy. And so this means that we again can try to exploit big dark matter experiments that have very low thresholds to detect them. So a burst, such as the one that I mentioned right here, that is very powerful from a collapse of such a supermassive star, can be seen with proposed big dark matter experiments up to Andromeda type of distances. So megaparsec scale. Additionally, historic bursts would also contribute to a new type of diffuse neutrino background in a similar way to the more familiar diffuse supernova neutrino background. And one can plot a band like this, subject to a variety of uncertainties, that there will be this new contribution to diffuse neutrino background from such events. Now, the diffuse neutrinos from past supernova, from past collapses of supermassive stars could also thus, in principle, contribute as an additional contamination source for dark matter surges. So this is the story about neutrinos and trying to use them with supermassive stars to try to explore the origin of supermassive black holes and the various pathways for the formation of them. And this brings me to the next topic, which is doing axion astronomy and axion spectroscopy with dark matter laboratories. And this is based on this recent study with Josh Abbey, Satoshi Shirai, and Evgeny Stadnik. And let me start with mentioning some general things about axion astronomy. Now, of course, axions are well motivated, of course, by the CP problem. There are also good motivations from more fundamental top-down theoretical perspectives, in particular, string theory motivated models. And the usual searches on axions focus on non-relativistic axion dark matter. But let me advocate for a novel direction, and that is doing axion astronomy with transients. As I just reminded you, using an example of supermassive stars, we can draw very interesting lessons from neutrino astronomy and apply them to axions. Not only from supermassive stars, but also what we know from supernova explosions and so on. In particular, we can do a general classification of neutrino astronomy as neutrino bursts, and these are basically strong emission events from some transients, such as supernova, supermassive stars. This can also appear from neutron star merger, and so on. And we can also identify that historic accumulation of neutrinos from such transient sources would give a new contribution to diffuse neutrino background. Of course, the most familiar one is the diffuse supernova neutrino background. And I would like to remind you that actually Super Kamiokande right now with gadolinium is within a factor of few of many models of the predictions. And within several years, we expect that observation of diffuse supernova neutrino background will occur. So some exciting things are happening along this direction. But having thought about neutrino astronomy, we can then draw a direct parallel and identify the corresponding axion astronomy items. One would be axion burst, and there are also a variety of transients that could be associated with this. For example, axion star explosions, axion emission from superradiance black hole bombs, or neutron star mergers, or you can come up with some other type of possibility. And then, by analogy with the diffuse neutrino background, one can also consider that accumulation of axions from historic transients would also result in diffuse axion background, which is, again, a new type of signature that has not been considered before. One can also do an analogy in the case of cosmic neutrinos. And for this, I would like to point to the paper of Jeff Dror, Nick Rod, and Hitoshi Murayama about cosmic axion background. And of course, here one can draw direct analogy with the cosmic neutrino background. So having all of this in mind, let's now focus more on illustrating using an example of axion star explosions, which is the main focus of this paper. And axion stars can arise within so-called mini cluster clouds, which are diffuse clouds of axions, but perhaps they have a dense core inside, which would be the axion star. Now, one can identify that there is some critical mass where this axion star would collapse. However, if you consider strong self-interactions in the potential, then the collapse will not go directly to a black hole, but rather there are actually some intermediate bound states where you will also have significant emission of relativistic axions during this process, and this is a so-called Bose nova. And this, of course, can be thought of as direct analogy, for example, of supernova for neutrinos. Now, very nicely, Levkov and Kachov actually did numerical simulations of this for the case of the QCD axion potential. Of course, one can consider some more general ALPS, but for the case of the QCD axion potential, numerical simulations have been done. And here on the x-axis, the k over m is moment over mass. So basically, with k over m bigger than 1, everything can be called so-called relativistic. And so, as you can see on this emission spectrum, there is a significant amount of relativistic axions being emitted. And these peaks correspond to the multiple rescatterings associated with the potential. So with 5 to the 4 potential, you will have 2 to 2 processes, 3 to 1, and 3 to 1, and so on. And all these are rescatterings happen during these processes, and so you will have multiple peaks. But the main point here is that you will see that within the spectrum of emission, there is a significant relativistic component. And just to give you some characteristic numbers, the critical, so this is in terms of the axion decay constant in terms of 10 to the 11 GeV, so this is F12, and then 5 is in terms of 10 to the minus 5 eV, just for some characteristic scales. So the critical mass could be 10 to the minus 11 solar masses, the critical radius 100 kilometers, the energy in the dominant peak of about 10 to 41 GeV, and the duration of burst is very short, around 30 nanoseconds. And the total energy loss is about 30 or 50% of the initial mass of the object. So it's very significant. Now we can then ask, if you have this signal, what can you do about the signal detection? Now, one thing is that you can have very significant axion density in your detector. And of course, this is very simply in accord with intuition. If you have explosion near your experiment, obviously you expect to see a lot of events. But this highlights again that from such possibilities, you can have a density within your experiment significantly larger than the ambient dark matter density. Additionally, one must take into account wave spreading effects because as the spectrum was being emitted at the location of the this Bose-Nova event, since different components have different momenta, the wave will spread, and so for your experiment to detection, you need to take into account these things. One interesting point is that relativistic axions also allow you to target different parameter space and conventional searches. So if your experiment is that for axion detection sensitive to particular frequencies, obviously when you have now non-negligible K, you can have a little bit different masses that you consider for your detection. And of course, the detection prospects depend on couplings. For some couplings, you can have modifications compared to dark matter, compared to ambient dark matter searches. For example, velocity enhancement is in principle possible. And then one can construct such a very general sensitivity plot where on the x-axis you can see the mass of the constituent particle, and the y-axis is the energy emitted in terms of solar masses into these relativistic axions. And then one can identify regions where you are more sensitive to test these couplings compared to ambient searches. And this plot is actually very general, and everything I'm describing right here can be readily applied to other possibilities in axion astronomy. So this kind of sets up axion astronomy in general. So you can do, for example, you can consider axions from neutron star mergers or whatever, and do exactly the same kind of analysis. Let me now mention a little bit more in detail that if you consider a very specific coupling, for example, coupling to photons, which is of course one of the most popular ones to consider, one can construct a more detailed constraint plot. And here on the x-axis is the mass of the axion. On the y-axis is the decay constant. This is the black hole superradiant bounds. Here are some bounds associated as you're approaching the Planck mass. And here are the various astrophysical bounds. The lines that go down right here, these are the limits of abracadabra type experiment, scaled, assuming different assumptions for these objects. And one interesting point to note here is that these limits from abracadabra type experiment go down and do not die with the axion decay constant. And this is in contrast to the conventional dark matter searches. And the reason for this is that while the coupling goes as 1 over f, so as you modify the f, obviously the limits also change. However, in the case of axion star explosions, the emitted signal goes as f on top, and so the two kind of cancel each other. And so actually you do not have a decrease in the overall sensitivity as you move down in f. And this also implies that perhaps relativistic axions from such transient sources might be a good way to probe different kinds of decay constants compared to the more usual searches. But what is more important, and this is of course a subject for future work, is that this also offers a way to probe the fundamental axion potential itself, which is challenging to do otherwise. In particular, this whole emitted axion spectrum that I mentioned from these events is very sensitive to what kind of potential you insert and what kind of self-interactions. So because of this, detection of relativistic axions from such sources can allow you to do axion spectroscopy. Of course, you can have new opportunities for multi-messenger astronomy, and here actually the yellow is the region where there's some signals associated with photons, and we also know that collisions, for example, of axion stars with neutron stars and conversion of axions in the neutron star magnetosphere and so on can also be associated with various signatures for photon coupling, and so there's new opportunities for multi-messenger astronomy with relativistic axions. And as I said, all this is just one particular example, but this sets up the axion astronomy in general. One can do exactly the same analysis with any kind of transient that you can imagine. And again, there will be a new kind of signal, which is diffuse axion background, which is yet another type of contribution to be studied further. Now, in the next topic, I would like to focus on another possibility that can be very well associated with the multi-messenger astronomy, and that is primordial black holes. So, of course, as we briefly discussed, seeds of supermassive black holes associated with astrophysics, the seeds of supermassive black holes and other astrophysical puzzles, as well as multi-messenger detections, could be manifestation of non-particle dark matter remnants from the early universe, primordial black holes. And let me remind you first about the status of primordial black holes briefly. So, of course, please see some nice reviews by Misao Sasaki, Bernard Carr, and others. And here is a plot looking at a specifically interesting parameter space of primordial black holes. On the x-axis is the mass in grams, or equivalently in solar masses. And on the y-axis is the fraction PBH make into dark matter. Now, the constraints on the left are set by Hawking evaporation. You do not want primordial black holes to have evaporated until today, but since primordial black holes emit in a whole particle spectrum, there's a lot of interesting signatures that you can think about for constraints in this region. Now, as you move farther to the right, there is a variety of constraints associated with microlensing, such as HSC and the ogle. Farther to the right are the constraints associated with gravitational waves. Of course, the connection between primordial black holes and LIGO are one of the main interests, farther pushing studies of primordial black holes. And even farther, there's various constraints which could be generally associated with various accretion emission associated with primordial black holes. I would like to point out that very interestingly, in the last several years, it has been appreciated there's actually an open dark matter parameter space where primordial black holes would constitute the entirety of that dark matter within this range, spanning several orders of magnitude. So there's many different ways you can make primordial black holes, and let me discuss one interesting possibility, and that is primordial black holes from bubble multiverse. And I will not discuss the details, but the rough outline of this mechanism is that it is, of course, very well motivated to consider models of multi-field inflation. If you have many scalars in your model, which is motivated from top-down perspective, multi-field inflation could be quite generic. And in such cases, if you have some generic complicated potential, the vacuum structure could also be quite complicated. And then it could also be conceivable that it might not be unlikely that as you're slow rolling during inflation, you can tunnel to various nearby minima, produce vacuum bubbles, which will expand. Now, if this process happens over some time, there's then a distribution of expanding bubbles, which recollapse and from outside observer point of view, make black holes. And so this is a generic mechanism of making primordial black holes, which are broadly distributed in mass. Now, we recently revisited this with some people at IPMU and UCLA, and this is just a toy potential illustration for this kind of setup. This is basically a tilted Mexican head with two fields. You start on top, you roll on the rim, and you can tunnel to the middle, making vacuum bubbles, which collapse to black holes. But this is just one toy example. But what is very curious is that perhaps such possibility of having a broad mass spectrum primordial black holes, for example, such associated with this exciting bubble multiverse possibility, has already been seen by Subaru HSC. Let me remind you that Subaru Hyper Suprime-Cam is doing microlensing of Andromeda Galaxy, and they detected a very interesting candidate event, as reported in the 2019 Nature paper. And this event is lying right here, and this is the HSC bound. And what is very curious is that, as you can see from this line right here, a primordial black hole dark matter lying in this open parameter space from this broad mass spectrum, which can arise in this bubble multiverse scenario, is consistent with both addressing all of the dark matter as well as the candidate event. And this is, of course, very exciting. And this also displays how one can use the tail of a broad distribution to indirectly probe the open parameter space right here. In fact, one can do even better. One can generalize the model a little bit further with some additional assumptions, and then simultaneously explain several more observables, which would be dark matter, HSC, but also LIGO and the supermassive black hole seeds right here. So, of course, if you can explain a lot of these simultaneously, this is very exciting. And upcoming observations by HSC, which are right here, will be able to definitively probe if such scenario is responsible for all the dark matter in this open parameter space right here. I would also like to note that one can think of other possibilities to do indirect tests. In particular, one can even indirectly test the recently reported nanograph gravitational wave signal using HSC by considering primordial black holes. In particular, if within from your early universe power spectrum, you can simultaneously make primordial black holes and stochastic gravitational waves, then this offers you an indirect way for HSC to test the nanograph signal through primordial black holes. So there's all kinds of indirect connections like this that you can consider and make. Now, let me talk a little bit more about the various interesting phenomenology in astrophysics that can be associated with primordial black holes. In particular, how one can make gold from these tiny primordial black holes opening in the lying in the open dark matter parameter space. Now, let me just remind you that the origin of heavy elements such as gold is a long-standing problem, is another long-standing problem in astrophysics. And the major responsible mechanism for this is thought to be so-called R process nucleosynthesis. And the idea there is that within some neutron-rich environment, you have some seed nuclei. And if the conditions are favorable, the neutrons are captured very fast on this seed, and you can build up a big atomic number. And of course, very likely this happens within the context of neutron star mergers. And we heard that the 2017 neutron star merger detection really advanced this problem. Now, neutron star mergers are, of course, great, but some recent analysis shows that perhaps they might not be enough. And this has been picked up by some science media saying that something is raining gold across the universe, no one knows what it is. And so there's a little bit of excitement along this direction. Well, let me discuss one elegant possibility how we can assist neutron star mergers, and that is by using asteroid mass black holes, making up dark matter, and then consider them within environments of significant dark matter density as well as significant neutron star density, for example, near the galactic center. And there, such tiny primordial black holes could be captured by neutron stars. And then as they're sitting inside the neutron star, they will eat the neutron star and cause emission. and the emission of this neutron-rich material from such primordial Hall-neutron star interaction would be very analogous to the neutron star mergers, and in such a way, such tiny primordial holes interacting with neutron stars can serve as our process nucleosynthesis gold factors. Now, curiously, neutron stars and white dwarfs are interesting primordial Hall aborters beyond just our process nucleosynthesis that I mentioned. For example, one can consider emission of positrons from such interactions and then tie them to the long-standing 511 keV galactic center axis. And I would like to point out that this actually could be explained fully just using usual neutron star mergers. And there's some very interesting work related to 511 keV signal, of course, by some of the local experts in Australia. There's also types of other signals that one can have that are a little bit unusual. For example, one can have a kilonova afterglow, but without a merger accompanying gravity wave. One can have fast radio bursts, which are right now a very hot topic, and the origin of them is still unknown. One can have perhaps gamma ray bursts without gravity wave emission. And what is more interesting is that one will have a population of transmuted solar mass black holes remaining after these events. And this just comes from the fact that as the small primordial black hole inside eats the neutron star, even if there's some emission, there will be a solar mass black hole remaining. And this brings me to the next topic, which is the origin of solar mass black holes. Now, solar mass black holes, and here I mean basically solar mass black holes below 2.5 solar masses approximately, they are not expected from conventional astrophysics because of the neutron star stability limit. But perhaps they can be primordial black holes, but maybe small primordial black holes eating neutron stars, transmuted solar mass black holes, which I just mentioned. But also in the literature, people have been considering accumulation of particle dark matter, which then collapses and again leads to a transmuted solar mass black hole. So there's all these kinds of possibilities. Now, very interestingly, LIGO has detected candidate event, as reported quite recently. So how do we tell the origin? Well, a very simple but powerful consideration is that transmuted black holes from primordial black holes or accumulated particle dark matter eating neutron stars should follow the neutron star mass distribution. So if you ate a lot of neutron stars, the neutron stars have some mass distribution, so your final black holes from these neutron stars should also have a mass distribution that tracks the neutron stars. Now, from astrophysics, from our supernova considerations and so on, we know what is the expected neutron star mass distribution. And from this, by comparing the LIGO detected events, we can already make very powerful statements without doing complicated statistics. Namely, that large solar mass black hole candidates are very unlikely to be from particle or primordial Hall dark matter interacting with neutron stars. And with further statistics, this will be further improved, but this already gives you a powerful idea of how to identify the origin of such curious events. Well, this also brings me to the next point of identifying the origin of black hole neutron star mergers. And this is from a paper with Misao Sasaki and other collaborators from 2 weeks ago. So this is a very new result. And of course, as we know, primordial black hole mergers have been associated with LIGO black hole gravitational wave observations, and this is a topic of very large excitement and active research. Well, recently, LIGO reported observation of first 2 black hole neutron star candidates. Can they be primordial? Can they be associated with primordial? Well, one thing to consider is that unlike primordial black hole mergers, primordial black hole neutron star mergers can only happen after star formation because you need to make neutron stars first. So here is a plot of a distribution in the the NFW profile for the dark matter within a galaxy, and here's the distribution of neutron stars. So by considering the combination of these 2 distributions, you can then identify how to make primordial black hole neutron star events and binaries from scattering of the two. So this is basically a two-body scattering, but from this distribution, you can already see that the neutron stars and dark matter are not very efficiently sitting on top of each other. And here you can also look at different galaxies, from the small galaxies to the big galaxy and so on. You can also consider such possibilities that perhaps within a supermassive, within the vicinity of supermassive black hole in the galactic center, there is a big dark matter over density, so-called dark matter spike. But once you do all these considerations and calculate your merger rates, you end up with a plots like this. So on the x-axis, on the left plot is the mass of the halo. So this is basically different sizes of galactic halos, from this small one up to the Milky Way size. And this is the merger rate per halo. And as you can see, compared to the black hole, PBH merger rates right here, which are these lines, the merger rates of primordial black hole neutron stars are subdominant. And the reason they have this different shape is that because this is associated with the amount of stellar material, because you're not just doing dark matter interactions like PBH, but you also need to interact dark matter with stellar material for primordial whole neutron stars. And once you calculate the total merger rates, assuming some cutoff in the integrated galactic halos, you will see that the rates of primordial whole neutron stars are always subdominant compared to, for example, PBH, and are always significantly below 1. 1 per year per gigaparsec cube. And what this demonstrates is that if the total primordial black hole neutron star rates for mergers are subdominant, the neutron star black hole mergers that have been detected, but also that will be detected in the future, are of astrophysical origin. And this is contrary to some speculations already in the literature that these could be PBH neutron stars. And this is a very powerful fundamental result, which also carries implications for multi-massive astronomy. Now, what is another curious fact is that even that this result is true, even if primordial black hole mergers can significantly contribute to black hole merger rate. And the reason for this is that even if in the late universe, which this is, the merger rates for PBH are small, they can receive significant enhancements from the early universe before star formation, which is something that PBH and S cannot have. So these are very interesting considerations and carry implications for the identification of the detected events. Well, what about intermediate mass black holes? Are they primordial? So as you probably know, LIGO also recently reported a very interesting 150 solar mass merger event, which is the first definitive intermediate mass black hole detection. Well, let me introduce to you a new cosmology-independent observable, and this is associated with heating and interactions with the surrounding gas. And the idea here is that as black hole is flying in the vicinity of gas, it will deposit energy within the surrounding gas through a variety of mechanisms. There will be some dynamical friction, which is basically gravitational drag. There will be some emission of photons from the accretion disk, and there will also be outflows and winds, which are basically some protons. But together, all these are just different channels of depositing energy. And once you consider this, one can ask that for a particular system, such as dark matter-rich galaxy Leo T, how do I balance the heating that I have with the inherent system cooling? And from this balance, one can actually, turns out, set very powerful constraints on primordial black holes. Let me just briefly mention that in this recent study, we also looked in detail at the emission of the various accretion disks. This plot like this that has not been before made in literature is quite helpful for identifying what kind of signatures are expected for primordial black holes interacting with surrounding gas. So for different primordial black hole masses and the densities of the surrounding gas, there will be different expected emission spectra depending on the type of accretion disks that you form in that system. Now, as I mentioned, one can set quite powerful constraints with these considerations, actually extending orders of magnitude in mass, and this is very interesting. I would like to note that there will be soon a work where the emission jets are also taken into account. Now, one can do a very similar analysis about the balance of heating and cooling by considering not the big black holes, which are right here, such as stellar mass intermediate mass black holes, but heating from evaporating primordial black holes. So these are tiny primordial black holes, but with Hawking operation, they emit a lot of stuff. And then again, you can do by analogy, very similar consideration of how much they heat the system versus cool the system, and set constraints on evaporating primordial black holes in such a way. And this brings me to the topic of discussion of how to explore evaporating primordial black holes with gravitational waves. So primordial black holes smaller than 10 to the 9 grams are unconstrained. They're so small and they have evaporated long ago, so they're not evaporating right now. So the question is, how do you explore such scenarios? Well, one line of attack in literature that people have been considering is this so-called dark radiation. And the idea here is that as primordial black holes evaporate, they will emit a bunch of products. These products will all contribute to dark radiation. And so this will also be interpreted as a change in delta N effective, and then look at the constraints in such a way. And recently it has been appreciated that spin of primordial black holes is actually very important for this. And the reason is that if primordial black hole is very highly spinning, it turns out the Hawking evaporation prefers emission of highly spinning particles. So you will suddenly have a strong emission of gravitons, which have spin too, and this could significantly impact delta NF for big spin. Another line of attack that people have been considering is that production of induced gravitational waves. And the idea here is that suppose in the early universe, you have an era where these tiny primordial black holes have dominated the universe, and then they decay. Now they decay, if it happens rapidly, that means that suddenly you have these bubbles of radiation happening everywhere, these primordial black holes decaying quickly. And so there will be big global pressure waves forming, and so there will be associated gravitational waves with big quadrupole moment. And again, you can interpret this as a change in delta NF. Now, it turns out that for this type of signature, the mass distribution is very important. And the reason for this is that if you have distribution of primordial black holes and mass, this could drastically modify the lifetime of the decaying primordial black holes. And because of the modification of the lifetime, there could also be not a very rapid evaporation. And so the gravitational waves associated with these bubbles of radiation will be small. So considering these two possibilities in this recent study with Guillaume Domenech and Misao Sasaki, we basically show that coincidence signatures between them could allow you to probe a broad class of primordial black hole parameter space for different models. On the left right here is the plot of delta NF, where on the x-axis is the mass of black holes, and here are the various constraints and the reach of CMBS4 upcoming experiments, and the blue line right here shows the delta NF associated with this dark radiation without significant spin of PBH. This is with significant spin, so you can see that spin is very important for this. And here, the slanted lines are associated with these induced gravitational waves, which I mentioned for a particular power spectrum. And the combination of these effects, as well as gravitational wave observations, can allow you to probe the distributions in spins and masses, and hence formation models of the very early universe evaporated primordial black holes, which are very tiny. So coincidence signals allow you to probe many scenarios over broad mass range. So let me summarize that large dark matter experiments can act as unique effective neutrino telescopes. There's a new window into astronomy and BSM physics, which is very exciting and complementary to the conventional neutrino experiments. There's also a very nice possibility of doing axion astronomy with transients that has not been well explored, and it paves a new direction for exploration complementary to the more conventional axion dark matter searches. One can perhaps gain insights into the fundamental axion potential new signatures, connection with multi-messenger astronomy. This is also now a Renaissance era in PBH research. Again, synergy with multi-messenger astronomy, new ideas for production signals and major puzzles. And this is now a very bright future for discoveries leveraging the astroparticle connection, which I believe all of these could be classified as. And before I finish, let me just briefly mention that actually on almost all of these topics that I mentioned, I'm organizing a big conference happening in Japan from December 7 and 10, hosted by Kavli IPMU, and you, of course, are all very welcome. So thank you very much.
Great, thank you very much for that fascinating and very very broad seminar. Let's have some questions. If anyone wants to ask, please just go ahead. If not, I will begin. So I'm interested actually in this this axion, these signals from these axion stars. Can you go back to the plot where you were showing these this plot of basically the photon coupling versus the axion mass? Yeah, this one. Okay, so I understand. So you were saying these blue regions are abracadabra, did you say? Is that?
It's abracadabra rescaled. Yes.
Yeah. Okay. And then, so you were like basically sort of looking for when the axions coming from these axion star explosions or whatever would have the same frequency that would be in the band that abracadabra would be searching for. Okay.
Yeah.
So did you take into account or think about sort of the shape of that spectrum? Because I mean, abracadabra are kind of looking for like they're looking for an axion line, with maybe like a spectral shape similar to the dark matter halo distribution, velocity distribution. So what would the spectral shape of this be? And would it be the kind of thing that, because abracadabra might, they may not initially be looking for transient, so they may throw out a signal which doesn't look like an axion and also then disappears. What sort of thoughts do you have about that?
Yeah, thank you for the very interesting question. So we have not done, so this basically was an idea paper. We have not done detailed spectroscopy analysis and consideration of the shape. So such things as coherence and so on are taken into account, but the discussion of shape has not been studied in detail, and this is something that we are interested in looking further. And indeed, as you point out, it would also be very interesting to make sure that these experiments do not throw out any signatures that perhaps look a little bit not familiar to them compared to conventional searches. So indeed, this is an interesting another possibility.
If I could just ask one final question about this plot. So you have these kind of different bands for the different. So this 10 parsec and 1000 AU. Is that the distance to the axion star?
Yes.
Okay. And do you have a feeling for like how close it? You mean, so you got these sort of three values. What do you know any kind of estimates for how close the sort of typical axion star might be if like you have 100% of the dark matter in axions?
Yeah, thank you for the very good question. Sorry, I went over this a little bit quickly. So the red lines right here actually are exactly this. So this assumes a particular distance, that explosion happens, let's say, in the time scales of 10 giga-years, which is the galactic time scale, and this is the fraction of dark matter. Now, no one really knows any of these quantities, so since we wanted to set up a sort of axion astronomy in general, we treated them phenomenologically. But depending on the assumptions, these lines will move around here.
I see. Yeah. Okay. Anyone else want to jump in before I ask another question? Okay. Well, I can keep going. Yeah. I thought it was quite interesting. So can you go to this plot where you were showing is the primordial black hole parameter space, and then you had this HSC star, and then your band for your predicted range of yeah, here we go. So what is it? Is there something obvious that I'm missing? Why is the star not in the band? Is this to do with like the mass function or something? It's like a
this plot might be a little bit confusing. So to account so as you can see, this band actually corresponds to allowed region for one candidate event. So what you do is actually you take the sensitivity and you integrate it over some mass range, and you ask what is the probability of getting one event. So because it is integrated, this line will be below this because it's integrated. It's not exactly on top.
I see. Okay. Yeah. Okay. Yeah, that's good. And then the next slide to this was very interesting. So you were suggesting that that you could explain the dark matter, this HSC event, the LIGO mass black holes, and potentially the supermassive black hole seeds. Can I just ask, sort of how much sort of work do you have to do to get this sort of green line which looks like that and covers all of those signals? What kind of how fine-tuned would you say that is?
No, that's a great question. So at this work, this was also a more phenomenological approach. So the shapes of the lines are shown right here, namely this shape right here and this straight line right here. So this is characteristic of the subcritical and supercritical bubbles within the context of this scenario. So there's these two possibilities, and they give this different shape. Now, if you do also assumptions about what happens during either matter-dominated or radiation-dominated universe, then you can also change things a little bit, and you can have such extensions. Now, to answer your question, all of these considerations will need to be, these several phenomenological parameters will in principle need to be directly mapped to a full particle model, which has not been done.
Okay, that's good.
So just to briefly touch up on this point, so such things as, for example, the bubble nucleation and so on, all this, transitions and so on, in principle, this needs to be calculated from a particle model. So
yeah. Okay, so maybe one final question for me, and then we can wrap up. So this neutrino background from the supermassive black holes, it looks a little unfortunate that it's so low. Do you think there's any possibility that would be detectable, or is it just going to be well outside of any future neutrino telescope? What's your feeling?
This is a very good question. So the issue is that no one knows pretty much anything about this. So this band that is shown, that corresponds to different assumptions about redshift distribution. So if you assume that supermassive stars are somehow tied to supermassive black holes, we know there's one supermassive black hole, let's say, within each galactic center, then you can try to normalize these things. But what is the redshift distribution of such collapses and so on? No one knows. So this band corresponds to some different assumptions about different possible models in the redshift distribution. Now, because the neutrinos are actually lower energy than supernova ones, which is of order 20 MeV, everything gets redshifted to even lower energy. So actually, these are the expected energetics. Even with assumptions on redshift and so on. So
but I guess so. Like if Super K is sort of at the cusp of seeing the DSMB, maybe just above the solar neutrino, because they're going to be drowned out by solar neutrinos presumably. So it has to be in that small window between the solar flux and the atmospheric flux. You're below
correct.
that, even below, even for the most optimistic one.
Indeed.
Yeah.
Exactly. Yeah.
Yeah, but yeah, cool. So yeah, that was all of my.
No, thank you for the great questions. Thank you for the questions.
Okay, if anyone has any final thoughts, they could just please just shout out. But if not, I will stop the recording.